Hello everyone, welcome to NPTEL MOOC course on electric vehicles. So let us start the next topic under this course, which is vehicle dynamics, modeling and simulation. So today we will cover the topic introduction to vehicle dynamics and tractive effort. So vehicle is a movable system and therefore many forces act on it, and the resultant force will decide the motion as per Newton's second law. The main motive force which moves the vehicle is obtained from traction unit or propulsion unit, and there are various forces which oppose the motion, such as gravitation force, air friction, the resistance offered by tire, etc. So, the total acceleration will finally depending on the rating of the traction unit as well as the mass of all the components. So, vehicle dynamics is very important and integral part of vehicle design. So, when we are designing a electric vehicle or any vehicle for that sake, we have to go in a two level approach. Since it is a complex system and is a huge system, we generally do a system level design followed by component level design. So, what we mean by system level design? In this design, the designer try to understand the requirements the vehicle need to deliver, and it will try to obtain and understand the specifications of the system in a broad way. So, what are the typical requirements of a vehicle is what is the acceleration, speed, range. So, these are the systems requirements which needs to be understood at first place. So, until this is clear, the vehicle design cannot start. Once the requirements is understood, we know broadly the ratings of the propulsion system, such as the specifications of power rating and energy requirements. Once this is done, the designer has to go for more finer design known as component level design. So, since we all know this, a electric vehicle is a multidisciplinary domain. Therefore, when we do component level design, we have to understand the rating of motor, which is generally done by electrical engineers, the rating of IC engine, which is done by mechanical engineers, the energy source, which is the domain of chemical engineers, power converters, the rating and the design is subject of power electronics engineers, and the control system, which is subject of control engineers. So, this all component level design has to be done by individual discipline experts, and they have to come out with suitable models. So, once this component level modeling is done, followed by a system level modeling, so this requires integration of the system. Then we go for the total simulation. The system is run using different iterations, such that the original design goals are met or satisfied. So, it is a iterative process, and so when we do the modeling of vehicle dynamics, there are two ways of doing it. One is longitudinal vehicle dynamics, the another is lateral vehicle dynamics. So, when the vehicle is moving in a one dimension, the dynamics required to be known is only longitudinal. But when you have more than one dimension to control, the dynamics required to be known as lateral dynamics. So, a normal vehicle, let us say a IC engine based vehicle, works on longitudinal vehicle dynamics. So, the vehicle has to move in one direction, and when the vehicle needs to be turned, that job is done by differential. So, the control person do not need to understand the lateral dynamics of the system a lot. On the other hand, when we are going for dual motor system of electric vehicle or in wheel type of electric vehicle, both the longitudinal and lateral dynamics has to be controlled by the individual electric drive trains. There the understanding of lateral vehicle dynamics is very important. So, it is a multi-dimensional way of modeling. So, generally when we go for a low speed vehicle, the first or the longitudinal vehicle dynamics is enough to be understood, but when we are going for very high speed operation, we have to understand the lateral vehicle dynamics as well for good control of the vehicle and road handling. So, what is tractive effort? The effort that is required to move the vehicle or propel the vehicle. So, this effort or force is generally transmitted to the ground for moving the vehicle to the driving axle and the wheels. So, let us consider a vehicle having a mass m which is moving at velocity v and going at a slope of angle theta. Then the typical electric tractive effort that is required to be accomplished is equal to the force required to overcome the rolling resistance, that is the resistance offered due to tire resistance and the road resistance. The vehicle also has to overcome the aerodynamic drag. So, this is the opposing force due to air pressure. Thirdly, we all know that when we are going on a slope, let us say on a flyover on a hill, the vehicle mass itself will act against the driving force. So, this is kind of a gradient force which opposes the motion and it has to be also overcome. Secondly, if the vehicle needs to be accelerated, those forces also needs to be delivered by the tractive effort. So, this force is absent when a vehicle is running at constant speed. So, let us try to understand these forces by means of a diagram. So, let us consider a vehicle moving on a slope which is at angle theta. The mass of the vehicle is m and the velocity is v. So, let us see that the velocity is v and the vehicle is moving up the slope. So, if we take this as the center of gravity, then the force due to the weight of the vehicle is mg, which is acting downwards. So, the total tractive effort, which we will denote as F T E, is equal to the gradient force because of the weight of the vehicle, which is F g. So, this is equal to V m g sin theta. The opposing force due to air, which is coming from the front of the vehicle because of the velocity of the vehicle that is moving up, is known as force due to air drag or aerodynamic drag. Also, the vehicle has to provide force due to tire friction or road friction, which is generally termed as F R R or F rolling resistance. So, this tractive effort F T E has to support all these forces, that is F g, which is force due to gradient, F R R, which is force due to rolling resistance, F A D, which is force due to aerodynamic drag, and also acceleration if there is a change in vehicle speed. So, this will be m into dV by dt, which is basically force due to linear acceleration. So, let us try to understand these forces slightly in more detail. So, let us try to understand the basic power, energy and speed relationship, which will be very handy for quick calculations of different forces and performance parameters. So, if we assume that the vehicle is travelling at constant speed of v meter per second, then the power required is equal to force into speed. So, P is equal to F into V, and V can always be written as distance by time. So, power can be written as F into distance by time. Similarly, we all know that energy is equal to power into time, and for a constant speed application, the energy can be written as energy is equal to power into time or power into distance by speed. So, this relationship is important because we can find the distance travelled for a non-energy input at a constant velocity with a power rating of P. So, these are some basic relationship which will be very handy in calculations. So, let us try to understand the first type of resistive force, which is known as aerodynamic drag, or we are terming it F A D. So, this is the force which the vehicle body encounters when the vehicle is moving at certain speed through the air. So, this is the friction due to air. So, the air drag is because of two types of drag forces. First is known as shape drag and second is known as skin friction. So, what is this shape drag? So, let us assume that a vehicle is moving in forward direction in some velocity v. So, when the front air is hitting against the vehicle front face, not all the air will be able to go behind the vehicle, and some of the air will be trapped in these regions. So, because of this trapping of air, a high pressure area will be created in the front portion of the wheel. Similarly, the wind which is coming towards the back side will also not able to fill all the gaps behind the vehicle, and there will be some regions of low pressure air. So, this pressure difference creates a drag which is known as shape drag. So, high pressure generally pushes the vehicle in the forward direction, while the low pressure area resists the motion of the vehicle. So, what is this skin friction? So, the air which is touching the vehicle body is also moving at the speed of the vehicle, but the air which is slightly farther from the vehicle is at 0 speed or standstill. So, the friction due to these two speeds of different airs which are close to each other creates a friction of air molecules, and therefore, is one of the reasons for aerodynamic drag. So, the aerodynamic drag is a function of the frontal area of the vehicle, the shape of the vehicle, and the different protrusions such as side mirrors, air ducts, air passages, spoilers, etc. So, this all will create drag forces. Air density. So, when the air density is high, the pressure due to air will be higher. The velocity of the vehicle. So, when the vehicle is moving at higher speed, the drag forces opposing it will be higher. Similarly, the velocity of air. So, if the velocity of air is high, which is opposing the vehicle, the drag will be higher. But in cases where the air velocity is supporting the vehicle, it will rather help in decreasing the drag. So, if we try to put the force due to aerodynamic drag in a form of equation, it will be like this. F A D is half rho C D A and square of velocity of the vehicle plus velocity of the air. So, this rho is density of air in kg meter cube. C D is a coefficient which depends on lot of vehicle design parameters, which is known as aerodynamic drag coefficient. V is forward velocity of the vehicle in meter per second, and V air is the opposing air velocity in meter per second. That is why is added here, but if the air velocity is supporting the forward velocity of the vehicle, it will be negative. So, it will be positive for opposing air velocity and it will be negative for supporting air velocity, and A is the frontal area of the vehicle in meter square. So, as we have seen, the coefficient known as C D, which is aerodynamic drag coefficient, is a vehicle design parameter. So, it depends on the type of vehicle design and the streamlining which is done to reduce the air drag. So, typical values or rather reasonable values are 0.3 for a good design, but it was as low as 0.19 for GM EV1. So, this is the first electric vehicle which was commercially available by 1995. So, it was very good design in terms of the drag coefficient. So, the effort should be done in vehicle design for electric vehicle such that this coefficient can be reduced. So, it is possible in EV because now the location of major components is more flexible in EV. So, it is not rigid as in IC engine based vehicle which are connected by mechanical means. So, we do not have requirements of cooling ducts because in a IC engine based vehicle there is a lot of heat loss and we require cooling ducts, but in a typical electric vehicle such kind of heat losses are not there. Similarly, the under vehicle pipe work is not needed in electric vehicle because there is no need to exhaust the heat energy coming out of the IC engine which was required in a IC engine based vehicle. Other transmission or design parameters which can be improved are you can have a tapered body or aerodynamic tail cone for reducing the low pressure in the back side, removal of side view mirrors, lowering the ground clearance, and having a smooth disc on the wheel, and there can be many ways this can be done, but these are some of the indicative parameters. So, let us see what are the typical values of this drag coefficient for different types of vehicle shapes. So, if we are considering open vehicle like this, it will have a high drag coefficient in the range of 0.5 to 0.7. Similarly, also for a van the range will be similar. For a regular vehicle which has a shape similar to this has slightly lesser drag coefficient which is the range of 0.4 to 0.5. In a wedge shaped vehicle, the drag coefficient can be further low in the range of 0.3 to 0.4. So, this is much better design compared to the regular vehicle. A very good streamlined design similar to this can have very low drag coefficient in the range of 0.15 to 0.2. So, in this design the wheels are inside the vehicle body. Another very good shape design is K-shaped design which is similar to this kind of vehicles. So, this drag coefficient is very high for trains, truck in the range of 0.8 to 1.5. It is slightly lower for a bus of 0.6, but the design of the bus can be improved by streamlining the design and lowering the CD by around 0.3, so that it will range of 0.3 to 0.4. For motorcycles, it is high in the range of 0.6 to 0.7. So, the design of electric vehicle is very important for reducing the aerodynamic drag. So, we have seen that the aerodynamic drag coefficient is a function of air density, which is rho kg per meter cube. So, we know that air density is a function of temperature, humidity and altitude. Therefore, the typical values of air density will vary from 1.5 at minus 40 degrees to 1.29 at 0 degrees to a much lower value of 1.12 at 40 degrees centigrade. So, we can see that there is a variation with temperature. and the values of this also varies with altitude. So, we can say that if we are operating at cold weather, the more power and more energy will be required from the traction unit compared to normal weather. For general calculations, we take a reasonable value of 1.25 kg per meter cube for performance calculation. So, if we try to understand the power required due to aerodynamic drag force, so it will be FAD into velocity of the vehicle, or we can also say that the power due to air drag is a function of velocity cube. So, this power requirement is very strong function of velocity. This relation is very similar to the power requirement in a typical wind turbine application. So, we can see that this force or this power requirement will be extremely high when we are working at very high speed or cruising speeds. So, this force will become dominant, and there should be every effort to reduce this power requirement. Similarly, the energy required due to aerodynamic drag force will be function of velocity square. So, we all know that energy is proportional to P into distance by velocity. Therefore, the energy is a function of square of the vehicle velocity. Similarly, if we assume a constant energy source or a limited energy source, we can say that the distance travelled or the range obtained is inversely proportional to the square of the velocity. So, higher the velocity of the vehicle, the distance will be lower. So, let us have a quick look at the effect of wind on range. So, if you want to understand the effect of wind velocity on the range obtained by electric vehicle. So, let us assume a EV which is operating at a vehicle speed of 100 km per hour with a drag coefficient of 0.2, frontal area of 3 meter square, air density of 1.2 kg per meter cube, and the energy available in the batteries is 10 kilowatt hour. So, what will be range if we having this kind of system parameters with no wind and with a opposing wind at 10 kilometer per hour. So, when there is no wind, the range can be calculated as 125 kilometer. So, how we calculate this? We have to calculate the aerodynamic force first. With non parameters. So, velocity we have to take in meter per second square. So, this is given in 100 kilometer per hour. So, 100 kilometer per hour will be equal to 100 into 1000 by this meter per second. The rest of parameter are in SI units anyway. So, it will give the force in newtons. Thereafter, we have to calculate the power due to aerodynamic drag, which is F AD into velocity. Then we can calculate the range as energy by power into velocity. So, this equation has given the range of 125 kilometers for no wind, and we want to find the range for a opposing wind velocity at 10 km per hour. This formula has to be slightly modified, and instead of V of 100 kilometer per hour, we have to take 110 kilometer per hour, because the wind velocity will now be added to the vehicle velocity. So, if we increase the together velocity from 100 to 110, the power will be higher, and therefore, the distance will be lower to a value of 103 kilometer per hour. So, we get a less range if there is opposing wind velocity. Similarly, if we want to understand the effect of vehicle speed on the power rating of the electric motor and the fuel consumption. Fuel consumption means the energy requirements from the battery. So, let us say if we have a vehicle which is normally driving at 100 kilometers per hour, and if we increase the speed to 120 kilometer per hour, what will be its effect on the power rating of the machine and the energy requirement from the battery. So, we know that power is a function of velocity cube, and energy is a function of velocity square. So, the power required or the power rating of the electric motor when we drive at 120 kilometer per hour in comparison to the power rating at when we drive the vehicle at 100 kilometer per hour is 120 by 100 cube. So, this comes to 1.728, which means that the rating of the electric motor should be 72% more if we just want to operate at a higher speed of 20 kilometer per hour. So, this is very significant. Similarly, when we talk about energy, so it will be 120 by 100 square, which is 1.44. So, the rating of the electrical battery capacity will be around 44% more. So, the effect of vehicle velocity on power and energy rating is very dominant and significant, and it can be seen from these calculations. Now, let us see the effect of the tire resistance and the road resistance on electric vehicle or vehicle performance. So, this force is known as rolling resistance force, which is FRR. So, all the friction forces or friction load forces which act on the vehicle movement are clubbed under rolling resistance force. So, this force is due to the deformation of the tire on the road surface when the vehicle is moving. So, this creates a resistance to motion. Secondly, all kind of frictions which is there in the drivetrains, such as bearings, gears, are part of this rolling resistance. So, this all has to be supported by the propulsion unit. So, we can say that this FRR or force due to rolling resistance is a function of weight of the vehicle, tire material and structure, and tire pressure. So, we all know that when the tire pressure is good, the resistance is lesser. Similarly, the quality of road such as road roughness and the material of the road. So, sometimes the material can be tar or it can be concrete or it can be a normal mud type of road. So, all this will affect the rolling resistance forces. Secondly, whether there is a presence of liquid on the road. So, when there is a rain, the friction offered by road becomes very less, and this is also a important parameter which has to be looked into. So, let us take a typical wheel of a vehicle. So, when it tries to move ahead with, let us say, velocity v, and this is the road surface, the front portion of the wheel will see a higher pressure compared to the back portion of the wheel, and therefore, the weight of the vehicle, which is denoted as P, will be shifted from the center to the front portion of the wheel. So, the pressure is higher on the front side. So, the opposing force which is overcoming this P will be shifted by a distance known as A, and we can see that normally the vehicle radius is r, but now it is compared to this road surface, now it is reduced from r to r d. So, when we want to calculate the force due to this pressure shift or the force shift, it can be done using following way. So, the rolling resistance moment because of this shifting can be calculated as this P into this A. So, this resistive moment has to be compared with the force due to rolling resistance into R d. So, F R R into the reduced resistance should be equal to P into A, and the P is basically the weight of the vehicle. So, F R R can be calculated as P into A by R d. So, the ratio of this A by R d is the coefficient of rolling resistance, which is known as mu R R. So, P can be mg cos theta if you are going on a slope of angle theta. So, F R can be written as F R R equal to mu R R, which is rolling resistance coefficient, into weight of the vehicle into cos theta, which is due to the slope of the vehicle moment. So, again this is put in a proper form. So, what are the typical values of rolling resistance coefficient mu R R for different types of vehicle and the road material? So, car tires on a concrete or asphalt road will have mu R R of 0.013. Similarly, the same vehicle on a rolled gravel will have a higher mu R R of 0.07. Tar road will have still higher mu R R of 0.025. Fields or mud kind of roads will have still higher mu R R of 0.1 to 0.35. But if we take the wheels on rails similar to trains and all that, they have very low mu R R of 0.001 to 0.002. Similarly, the truck tires generally are designed such that they have a lower mu r r if they are moving on a concrete or asphalt road. Typically, mu r r is independent of speed, but it has a very weak relation to vehicle speed, which can be equated as a function of velocity. Mu r r at known velocity is mu r r 1 plus velocity by 100. So, this empirical formula can be used for simple vehicle performance calculations. So, we have also discussed that the tire pressure is important. So, tire pressure, as you might have seen, is not the same for all vehicles. So, so different vehicle manufacturers give different pressure to be filled in their tires. So, why it is so? Because a good vehicle design generally looks for a low center of gravity of the vehicle, and if somehow in the design the center of gravity is higher, then it will create problems during turning and road handling at higher speeds. So, therefore, those kind of vehicles suggest a low tire pressure such that the center of gravity can be lowered. So, let us see the third kind of force which opposes the vehicle moment, which is known as gradient or hill climbing force. It can be also known as gradient resistance force, so which is generally denoted as F of G. So, we have discussed that because of the vehicle weight and the slope of the vehicle moment, the force due to gradient will be mg sin theta. So, this force will be 0 when the vehicle is moving on a flat road. So, when we are climbing flyover or a hill, this force is positive. So, in this case the electric machine will be operating as a motor, and we are undergoing a motoring operation. But when we are coming down a flyover or we are coming down a hill, this force is negative. So, if this force is negative, it means it can be observed. So, the electrical machine can now work as a generator, and the energy can be recovered from the wheels such that a safe speed can be maintained, and this energy regenerated can be used to charge the battery. So, all these forces can also be put in terms of equation which is known as vehicle road load forces. So, there is the equation which is known as force equal to A plus BV and CV square. So, it gives a empirical formula such that the total force is a function of velocity, curved velocity and independent of velocity. So, in this way it covers all the forces we discussed. So, generally the A is rolling resistance, which is a very weak function of speed. So, it takes care of basically rolling resistance force. Secondly, there are force due to spinning of and rotational losses. So, this is very low in any vehicle. Similarly, the constant C denotes the force due to aerodynamic drag resistance. So, this we know that the force due to aerodynamic drag is a function of square of the speed. So, this kind of the C coefficient denotes aerodynamic drag force. So, ABC parameters are or ABC coefficients are generally measured by a test known as coast road test, which is done by driving a vehicle at 120 km per hour speed and then bringing the vehicle to neutral. So the vehicle will move from the speed of 120 km per hour speed and it will slowly come to stop. So these parameters will be obtained by measurements. So this is a necessity in some of the regulated agencies in United States, where the vehicle manufacturer has to give these parameters for any vehicle they want to launch in US. So these parameters or coefficient is a simple way of putting the forces due to air drag, due to gravitational force or due to rolling resistance in terms of simple coefficient. So if you want to estimate the range of EV, let us say we have a EV and we know the ABC coefficient of that EV, and we want to estimate the range when the vehicle is driven at, let us say, constant speed of 100 km per hour for a known battery energy capacity, let us say it is E. So we will take this coefficient and calculate the power, which is Fv into velocity, which will be Av plus Vb square plus Cv cube. Then since we know the energy capacity of the battery, we can calculate the time required such that the total energy capacity will be exhausted. So it will be energy by power. And since we know the velocity, we can calculate the distances, velocity into time. So this simple calculation will enable us to estimate range for any EV with known battery capacity, speed and the ABC coefficient. So lot of data is available at this website, which is epa.gov of the US government, where all the ABC parameters and all emission and fuel consumption data is available for each electric vehicle and hybrid electric vehicle. So this is very handy data for any performance calculation. So EPA stands for Environmental Protection Agency. So gradability is one of the very important parameter which the vehicle manufacturer has to give in the data sheet of the vehicle. So what is this gradability? So it is the maximum slope or the grade which the vehicle can go from the maximum force that is available from the traction unit is known as gradability. So when we want to calculate the gradability, basically we are calculating the maximum slope the vehicle can go safely. So in calculating the gradability, we generally assume few things, that we are assuming that the vehicle is moving very slowly, almost 0 speed. So the force due to aerodynamic drag and rolling resistance is neglected. Acceleration is 0 because velocity is almost 0, and we are applying the maximum tractive force that is available from the propulsion unit. So at these conditions, so basically if we say this is center of gravity, so the tractive force is supporting only the gradient force, which is mg sin theta. So gradability is calculated as a ratio of rise to run or tangent of the slope angle. So basically it is gradability, you can say, is equal to tan theta of the slope. And if you want to give this data as percentage data, then it will be 100 into tan theta. So, how to calculate this data from this equation is, let us say once we know sin theta. So, sin theta is FTE by mg. So, we can say that this is FTE and this is mg. So, in that case this will be square root of mg square minus ft square. So, we can write this maximum percentage grade as 100 into tan theta, which is nothing but tan theta is FTE by square root of mg square minus ft square. So, generally the percentage grade is 100% for a slope of 45 degrees. So, for a 6 degrees, which is quite a standard gradability factor, the percentage grade is around 10.5%. So, we have seen the opposing or resisting forces which oppose the vehicle movement, that is aerodynamic drag, rolling resistance and gradient forces. But if you want to accelerate the vehicle or change the vehicle speed, we need to also provide the force required for acceleration. So, let us see the force which is required for linear acceleration. We all know that if we want to accelerate the vehicle and provide dv by dt, we have to provide force which is we can say as F force due to linear acceleration as mass into acceleration or m dv by dt. So, for acceleration we have to also support angular acceleration, which is we generally say as F into AA. So, this force is required to support the torque that is needed to spin the rotating parts within the drivetrain. So, let the electric motor is rotating or the gears are rotating. So, they also needs to be covered and under the force required for acceleration. So, we all know that if we have a let us say the moment of inertia because of the machines or any drivetrain transmission system, we can say the torque required is equal to moment of inertia into d omega by dt. And if you know the radius of the system, we can write as j by r dv by dt. But we want to convert this torque into corresponding linear force, it has to be divided by resistance, and then this formula becomes FFA equal to j by r square dv by dt. So, let us summarize the total tractive effort which is required to support the vehicle and accelerate the vehicle, and by providing the force due to resistive forces and due to acceleration. This is opposing forces and this is aiding forces. So, if we write these things in terms of formulas, it will be like this. So, this total tractive effort can be also be written in terms of ABC coefficient, and then it will be like this: A plus mg sin theta plus bv plus cv square plus acceleration forces. So, when the vehicle is operating as motor for forward motion of the vehicle, let us say we require a tractive effort of Ft moving at velocity v. So, for this to be obtained, we require a torque known as T axle and omega, which is omega axle. So, this linear forces and velocity has to be converted to torque and omega, which is angular mechanical forces. So, this T axle and omega axle has to be obtained from the electrical motor, and the power will go from battery electrical motor to the wheels. So, we can see that the direction of force velocity are on the same direction, and also the direction of t axle and omega axle in the same direction. Similarly, the T m and omega m also is in the same direction, because the power is flowing from the battery to the wheels. But when we are doing the braking operation and trying to recover the energy from the wheels, the torque axle and omega axle will become opposite. The vehicle will continue to move in the same direction. So, the omega axle still retains the original direction, but the torque applied to the axle will reverse now. Similarly, in the motor side. So, the power is transferred from the wheels to the battery from the electric drive train. So, the power is negative here. So, the power is flowing from here to the battery. So, that is all in today's discussion under the topic of tractive effort within vehicle dynamics. So, in our next interaction, we will try to do some simulations using basic programs and try to understand the effect of various forces and try to calculate the power and energy requirement for, let us say, different slope conditions, different vehicle speed conditions, wind velocity conditions, and different mass of the vehicle, and all these type of different parameter variations can be checked and simulated by simple programs. So, we will discuss and these things in the next interaction.